Here I'm going to give a brief introduction to the topic of maximum likelihood estimation, which is a very important topic in statistics. So the setup is like this. Suppose we have a random sample, some random variables x1, x2, xn, that are IID from some distribution f of theta. So recall IID means independent and identically distributed, right? So it means that each random variable is independent of one another and they're identically distributed. They all come from the same distribution, which I've called here f of theta. So you could imagine it could perhaps be a normal distribution, or it could be an exponential distribution. And the distribution is parameterized with some parameter theta here, right? So like for the normal distribution, it has two parameters typically. It's got a mean and a standard deviation. So that would be your parameter of the distribution. But you look at the exponential distribution, on the other hand, that generally just has one parameter, which is a rate parameter lambda. Okay, so the setup is that we have some data from a distribution that has some sort of parameter, and also suppose that the PDF of a random variable from that distribution is just denoted f, like this. This is the probability density function, the PDF, probability density function. Right, so given this, the parameters in the distribution are often unknown. If you think about in many real-world examples, if you have some sort of data from a distribution, it's quite common that you don't know what the true mean is of the population, or what the true standard deviation is, or what the best value for the rate parameter is in the exponential case, for example. So it's quite common to not know what it is, and a very natural question that then emerges is, given the data, what is your best estimate for what those unknown parameters are? And that's exactly the type of question that maximum likelihood attempts to answer. And it does this using what is known as the likelihood function. Right, so I'm just going to define some terms here. We've got this idea of the likelihood function. Right, the likelihood function is denoted like this: L of theta is called the likelihood function. And it's just equal to the joint density of the random variables. Is the joint density of the random sample, I guess, the random sample x1 through to xn, but it's treated as a function of the parameters. So you view this as it's the density, but you think of the density at a specific parameter value. So if you think about this intuitively, what it means is that given any specific parameter value, so given any sort of theta here, the likelihood function gives you some indication of how likely those parameters are to have been observed. Right? So we have some data, I look at a specific parameter and it tells me how likely it is to observe that. So quite naturally, a good idea for what the best parameters to choose could be, your best estimate for the parameters, could be to choose the parameters that maximize the likelihood function. And so that's all maximum likelihood is a maximization of the likelihood function, which is the joint density of the random sample. So I'll write that down here. So the maximum likelihood estimate, which is often abbreviated to MLE, the MLE, the maximum likelihood estimate of the parameter theta. And I'm calling theta a vector here because it could be two parameters. So like for the normal distribution I said before, it's a mean and a standard deviation, but it could also be one parameter, such as the exponential is just one, right? So the MLE of theta, the unknown parameter theta, is the value theta hat, it's denoted theta hat, such that the likelihood at theta hat is the maximum of the likelihood function. So you could write that as is greater than or equal to the likelihood at theta for all other values of theta in your parameter space, which is usually denoted with an omega, if you're familiar with that. So it's just the value that maximizes it. So maybe I'll write it at the bottom, the value that maximizes the likelihood function. Okay. So to do this, how do you find the maximum of a function? Very often the technique is to take the derivative and set it to 0. Of course, this isn't the only way to maximize a function, and there are some functions that maybe are maximized at the endpoints or at points of discontinuity. However, generally, you take the derivative and set it to 0. However, one thing is that these likelihood functions can often be quite difficult to take the derivatives of. And so one thing that you often do is you don't work with the likelihood function directly, but you work with the log likelihood function. So that's just the natural logarithm of the likelihood function. So I'll write this as a note. It is often easier to maximize log of the likelihood instead of just the normal likelihood function. And furthermore, I won't write this down, but there are quite a few useful properties of the log likelihood function specifically. And so it is very, very common to want to compute the log likelihood function. Also, something important to think about is why we allowed to also maximize the log. And if you think about it intuitively, what does log look like? Log is a monotone increasing function, right? So I'll draw a little picture up off to the side here. If you imagine what log looks like, if I put in here sort of x and y, then the natural log looks something like this. It's a monotone increasing function. It only ever increases. So if you maximize a function, that's just the same as maximizing the log of the function, because log will preserve those inequalities. Right? So maximizing the log likelihood is exactly the same as maximizing the likelihood, but generally it is usually easier, and it also has some desirable properties, which I'm not going to get into here just due to lack of time, but there are some desirable properties of the log likelihood function. Okay, so with all of this, then how do we maximize it? So I touched on this before, but usually that's by taking the derivatives and setting it to 0. Right? So to maximize the log likelihood, so to maximize the log likelihood, you can take the derivatives and set it to 0. So to maximize the log likelihood, set the derivative of the log likelihood with respect to your parameter, set it equal to 0, right? So the parameter could be a vector here. If it's a scalar, then you're just maximizing a function with respect to a scalar, which is something I hope everyone's quite familiar with. So say your function could be some sort of arbitrary function like this. You maximize with respect to a scalar. So sorry, it's there's only one axis. It's just the function can be drawn in 2 dimensions. So you just take the derivative with respect to your one parameter and set that to 0. If there's more than one parameter here, then I'm just using this as a sort of loose notation. I guess strictly speaking, you could write it as equating the gradient vector with respect to 0 to the 0 vector. So this is like setting all partial derivatives equal to 0. So if you recall, sort of at UQ, this would be content covered in Math 1052, I believe, /1072, where you maximize a multivariate function when the gradient vector is equal to 0. Right, so that's all we have to do. to find the MLE, we have to solve when the derivative of the log likelihood is 0. And usually these functions are quite well behaved. There will usually only be one turning point, so we don't have to worry about multiple turning points and things like that. However, of course, there can be counterexamples and more complicated situations. Also, I just want to, on the realm of covering a bit of terminology, I just wanted to mention here that the derivative of the log likelihood function, this is something that's very commonly done, and so it does have a name. This is called the score statistic. So I'll just write it off to the side as well, because this is important to remember that this score statistic, S, is just equal to the derivative of the log likelihood with respect to the parameter theta. And when you set the score statistic equal to 0, then, so this whole equation here, when you set it equal to 0, that's called the likelihood equation. So we're solving for the maximum likelihood estimates. We're solving for the maximum. So that's called a likelihood equation. Okay, so this is a little bit abstract, So I think the best way to really conceptualize this is with an example. But I wanted to go through it in the abstract first, just to get a high mental picture overview of what we need to do or what we're planning to achieve. And then we'll apply it to a specific example. So I was thinking we'll do the exponential distribution first. This one's not too difficult, so I'll go through this example. So here we're supposing we've got data from an exponential distribution. So we've got x1, x2, up to xn. We've got n samples that are IID, independent and identically distributed, from an exponential distribution parameterized by lambda. Okay, and recall what the probability density function is for a exponential distribution. So the probability density function is fx is equal to lambda e to the negative lambda x, right? That's the probability density function for a exponential lambda distribution, right? Okay, so we've got that. Now, let's look back at the notes above here. The next step that we want to do is we want to find what the likelihood function is. So in this case, the likelihood function, L of, and I won't put theta here, I'll put the parameter. So in this case, the parameter is lambda. L of lambda is equal to, and I said before, it's the joint density of your random variables. So given that the random variables are IID, this is very important, they're IID, so that means that the joint density is just going to be equal to the product of the individual densities, right? So that's a property of independent random variables, is that the joint density is the product of the individual marginal ones, right? So that means that the likelihood of theta, which is the joint density, is just the product of the individual densities. The density is lambda e to the negative lambda x, right? This is the density function. Across all of your samples, so j equals 1 to n. So this should be xj here, right? So it's the product of all of those. Okay, and then let's see can we simplify this likelihood function? Let's see if there's anything we can do here. Well, this lambda doesn't depend on j, so I can pull it out, lambda to the n. And an exponential, if you have lots of exponentials being multiplied together, then the powers add, right? It becomes additive in the power. So we get e to the, this becomes a sum. So we add up from j equals 1 to n of negative lambda to the xj. And I could simplify that a little bit further, just write that a bit neater. So we've got lambda to the n, e to the, I can factorize this out. So this can just come out of the sum. So it's negative lambda sum j equals 1 to n of xj. Okay, so that's the likelihood function. Now we could try to maximize this. However, as I said before, it is often quite useful to instead maximize the log likelihood. And as I also said before, there are some useful properties of the log likelihood. So that's what we're going to do here. We're going to find the log likelihood. So we've got a likelihood. The log likelihood is just the log of the likelihood function. So I take the log of both sides, put some big brackets here. We've got lambda to the n, e to the negative lambda, sum of the xj's, j from 1 to n. Okay, so using your log laws here, we've got log of a product, so I can split up the log into log of lambda n plus, times log of e to the negative lambda sum j equals 1 to n of xj. And my apologies, that is a plus. So your log laws, if you have log of this plus log of that, that becomes a multiplication inside the log, right? So we've got this as the expression here, and we can simplify a bit further here. So we've dropped the n log lambda, log exponential, they cancel, so minus lambda sum j equals 1 to n of xj, right? Okay, good. Now we compute the score statistics. Remember, the score statistic is just taking the derivative of this with respect to lambda. So I take the derivative of the log likelihood function with respect to lambda. That's equal to, if we look over here, the derivative of this with respect to lambda is n over lambda. And then here, the lambda becomes just a minus 1. And then we've got the sum here. So remember, because we're taking a partial derivative, the this sum here is just treated as a constant with respect to lambda. So the lambda just derives to a -1 and the constant stays there. Okay, so this is what we've got. And we want to solve for the MLE. So that means we just solve for when this is equal to 0. So when this is 0, that will be when our lambda is equal to its MLE. So when this is 0, then we can write lambda as the MLE. So I'm going to denote that with lambda hat, because lambda hat is the value of lambda such that the score statistic, this left-hand side is the score statistic, score is 0. So n on lambda hat minus the sum j equals 1 to n of xj. All right? Now we can try to solve this for lambda hat for our estimator. So I can add the sum to the other side, and I'll just write it this way. So we've got n on lambda hat, and then adding the sum over, we've got sum j equals 1 to n of xj. And then taking the reciprocal and multiplying the n over, we then get this. J equals 1 to n of xj. So I just took the reciprocal and then multiplied the n across, right? Okay, good. So this is our expression, and this is our estimator for lambda hat, or more specifically, this is our maximum likelihood estimator. So what's this saying? It's saying that if you have some data from an exponential distribution like this, then it's saying that your best estimate of the unknown parameter lambda is to do this. It's to take the sample size and divide that by the sum of all of your observations, right? And I could write this in a slightly nicer way. So n over this is precisely equal to 1 over x bar. If you recall, x bar is just your sample mean. So this is just the flip of your sample mean, right? Because I'll just write it off to the side, but your sample mean is equal to the sum j equals 1 to n of xj over n, right? That's your sample mean. So 1 over that is going to be equal to this expression here, right? Okay, so that's great. We've found using maximum likelihood estimation that this is the optimal choice for that parameter, that this is the value of lambda that will maximize the likelihood of the data coming from that distribution. Okay, to do a little bit more practice, I'll do one more example. So we'll do it in this time instead with the normal distribution. So this one's a little bit trickier here. We've got two parameters in the normal distribution, but I think it's worth doing because it shows you how you do it with a two-parameter case. I remember when I first learned this topic, being a bit confused how it extends to something like that. So I think it's worth going through it now, even though you may not have had much practice in this, because I think it helps show you how this works in other cases. Okay, so I'll go here and we'll do another example. And so this time we're doing from a normal distribution. So suppose we have x1 through to xn, which are again, they're IID distributed, but this time from a normal distribution, mu sigma squared, right? So this time we've got two parameters. In fact, I can denote that I could say that our parameter theta, like this, theta is just equal to the two parts. There's a mu and there's a sigma squared, right? Usually written as a column vector, so I just put a transpose here, but not strictly very important, right? So this is what we have, and we want to try to find what is the likelihood function. So the likelihood of our parameters, which in this case I've called with this vector theta, it's equal to, and it's the exact same process as before, so it's the product of the marginal distributions. It's the product of the density of each term, and that's by independence. Since they're independent, the joint density is just equal to the product of the marginal densities. And now, recall what the density function is for a normal distribution. So for a normal distribution, the density function is 1 on square root 2 pi sigma squared exp negative 1 over 2 sigma squared sum from j equals 1 to n of xj minus mu squared. Right, so this is the probability density function. So actually, I'll label it. This part here is the probability density function for data from a normal mu sigma squared distribution. Okay, and this is a very important formula to remember. If you don't remember this, if it's not one that you do remember, then it is worth engraving into your memory if statistics is an area that you want to look into, because it just shows up all the time and you need to be able to recall it quickly. So anyway, so this is the function, and we're multiplying n copies of this for each different term xj, right? So my apologies here. This is the sum of xj's. For a single observation, it's just this. I was actually getting a little bit ahead of myself. So let me actually shorten that bracket. Yeah, my apologies for that. So this is for a single observation. I was getting ahead of myself with a sum in there, and you'll see where that comes from in just a second, because in this next step of working, what we're going to do is, because we're multiplying these together, we see if we can simplify this, right? So this first term doesn't have any j's in it, so I can just take it out and just raise it to the power of n, right? Because we just got n copies of this being multiplied together. So we've just got 1 on square root 2 pi sigma squared to the power of n here. Then we go to this next bit, the exponential part, and if you have product of exponentials, that just becomes a sum inside. So it's very similar to what we did just above here. We had a product of exponentials, and it just became a sum inside the exponential. So the exact same thing here. It's just going to become a sum inside the exponential. And there are no j terms in here on the sum, so I'm also going to just factorize that out. And the only part we're summing over is over this, the xj minus mu squared. Right, so what we've done here is we've just brought in the sum because it was a product, and if you multiply exponentials together, it becomes a sum in the exponents. So we've got a sum inside, And I just wrote this outside of the sum because it doesn't have any j's in it, so you can always factorize that out, right? And so this is the expression we get, and that's why I sort of accidentally drew in a sum here before. I was just thinking ahead to the next step, right? So this is our expression for the likelihood function. And we're going to continue with exactly the same process as before. So we found the likelihood function, we simplified it. The next step is we're going to find the log likelihood function. So we're going to take the log of both sides. So on the left-hand side, we've got the log of the likelihood function. And then on the right-hand side, we're going to take the log of this side. So the log of a product becomes logs of the sums, right? So we've got log of this first term here, 1 on square root 2 pi sigma squared to the n, and then the second term here, the log is going to cancel the exponential. So we're just going to be left with minus 1 on 2 sigma squared sum from j equals 1 to n of xj minus mu squared. Right? That's because the log of an exponential cancels, right? So we've got this, and then from here, we can simplify a bit further. I'm skipping steps a little bit here. I'm assuming that you're quite comfortable with this sort of algebra, but if it is confusing, feel free to just pause it and maybe go through it in a little bit, in a few more steps, right? But here we can simplify this. This is just this term to the power of negative a half, because it's 1 over a square root. And there's the n, so we can pull the n out. So we've got negative n over 2 log 2 pi sigma squared. And then over here, this term stays the same. This one is good as it is. So we've got this, j equals 1 to n of xj minus mu squared. Okay, great. Now that we've done that, we're continuing with the same steps. We're going to take the partial derivatives. And in this case, because the parameter theta has two parts, we're going to take two different partial derivatives, one with respect to mu and one with respect to sigma squared. So one for each of our two parameters, right? So this is unlike before we need to do one partial derivative because there's one parameter. Here we'll do two, right? So I'll take the partial derivative of log L of theta with respect to mu first. And if we look on this side, what's the derivative of this with respect to mu? Well, there's no mu in the first term, so that goes away. Here there is a mu, right? And the derivative is a linear operator, so it can act inside this sum. So if we take the derivative here, what's going to happen? The 2 is going to drop. It becomes a 1, and then we multiply by -1 by the chain rule. So I'll write that out. What have we got? We've got here at the front the 1 on 2 sigma squared, and then the sum j equals 1 to n, and then we take the derivative inside the sum. So the 2 is going to drop. The xj minus mu, the power decreases by 1, so instead of 2 it's now just 1. And then we have to multiply still by the derivative of the inside. So that's just sort of applying the chain rule inside here. And okay, so we've got that. And then we can simplify a little bit here. I can just take the 2 out. It's going to cancel with that too. The negative's also going to cancel. So we get 1 on sigma squared, sum j equals 1 to n of xj minus mu, right? Okay, it's a j there. Yes, okay, so that's what we've got. And now to solve for the MLEs, we just need to solve for when the score statistic is 0, right? So this is the score statistic. As I said, there are going to be two different parts to it because we can take the partial derivatives with respect to mu and with respect to sigma squared, but we're just working with mu right now. And so we'll set this equal to 0. So 0 is equal to 1 on sigma squared, sum j equals 1 to n of xj minus mu. Well, technically what I should say is that the score is equal to 0 when the parameters are the MLEs. So I should really put some hats on here because it is when you use the MLEs, the score statistic is 0, right? The score statistic isn't always equal to 0. It's equal to 0 when you use the MLEs. So we get this equation, right? So this is, if you recall from before, I said that you have the likelihood equations. And because there are two parameter vectors, we're going to have two likelihood equations. So this is our first one, likelihood equation number 1. And then we're going to take the partial derivative with respect to sigma squared and get a second likelihood equation. So I'm going to do that now. Yeah, I'll explain in more detail later, but I'll do that now. We'll just take the next partial derivative. So I'm going to take, instead of taking the partial derivative with respect to mu, this time we're going to take the partial derivative with respect to sigma squared. Now, something important to note here is I'm deriving with respect to sigma squared as a whole block. This is important. It's much easier when you do this to derive with respect to sigma squared as opposed to deriving with respect to sigma. At the end of the day, it doesn't make a big difference, but it does, the maths does turn out a little bit cleaner if you do it this way. But just important to understand conceptually. So we're just treating sigma squared as a single block. Just imagine it's a single block, right? Just imagine that this is just one symbol. Okay, so let's go back to the equation. We're deriving with respect to sigma squared. So this is our score statistic here. Sorry, this is the log likelihood. And to derive with respect to sigma squared, there's a sigma squared in here. So what's the derivative of that going to be? There's a constant out the front, that just stays, the negative n over 2. And then here we're going to have 2 pi on the top, because the sigma squared disappears, over the original, so 2 pi sigma squared. Okay. Then over here, again, the derivative with respect to sigma squared, that's going to be plus 1 on 2 sigma to the 4, I think. I always, whenever I have something on the bottom of the fraction, I always like to think of it in terms of negative exponents. So maybe I'll just write off to the side here. What is this equal to? So we've got negative 1 on 2 sigma squared. That's just equal to negative a half sigma squared to the negative 1, right? So this is the same thing. So that means if you take the derivative with respect to sigma squared, then what happens? Well, the negative 1 drops, so it cancels with that one, so it becomes positive a half, and then sigma squared, and then the exponent decreases, so negative 2. So that should be 1 over 2 sigma to the 4, right? Which is what I said over here, but I always mentally kind of go through this process. Okay, so then you get that exponent, and the term after remains there, so it's a constant with respect to the derivative, so we still get this term, j equals 1 to n of xj minus mu squared, right? And then we can solve for when this is equal to 0 to get our second equation, which form part of these likelihood equations. So this is 0 when the MLEs are true. So when the values are equal to the MLEs. So we can simplify this a little bit. The 2 pi cancels with that 2 pi. Let me write that in black so it's easier to see. Those cancel. And so you're just left with a negative n on 2 sigma squared. And I'll put a hat here, so MLEs when it's equal to 0, plus 1 on 2 sigma to the 4 hat, and then sum j equals 1 to n of xj minus mu hat squared. Okay, so this forms our second likelihood equation. I'll put that in another green box, label it number 2, and so these are our likelihood equations. And now we can solve these simultaneously to find the parameters mu hat and sigma squared hat. Now you will notice in this specific example, we can actually solve number 1 straight away without needing to do any sort of substitutions or things like that. So this one actually works quite cleanly. If I just go from equation 1, let's see what we can do. So I'm just going to rewrite equation 1 down here. It's equal to 0, or the equation 1 tells us that 0 equals 1 on sigma hat squared sum from j equals 1 to n of xj minus mu hat squared. So of xj minus mu hat squared. Right, so when is this equal to 0? Well, we can just cancel off this term, it doesn't matter, multiply it to the other side, right? So 0 equals sum j equals 1 to n of xj minus mu hat. And my apologies, there's not supposed to be a squared on here. I copied the equation wrong. The squared disappeared when we were deriving with respect to mu, right? If you recall, over here, we take the derivative with respect to mu, the 2 dropped. So there wasn't a square anymore. So this is what the equation was. Okay, so this is looking good. There's no more sigma hat. We just need to rearrange this to be in terms of mu hat. So 0 is equal to, and then what do we have here? So I can split up this sum to be the sum from j equals 1 to n of xj minus n copies of mu hat. So mu hat didn't depend on the sum, so I could just extract it out, but we're subtracting n copies of it, right? Because it's a sum j equals 1 to n. Okay, so then I can just add this to the other side. So n mu hat is equal to the sum j equals 1 to n of xj, which then implies that mu hat is equal to 1 over n sum j equals 1 to n of xj, which you might recall is just equal to the sample mean. So this is quite intuitive, but it is still quite sort of satisfying to arrive at it mathematically. So what we've shown is that the best choice for the population mean, your best estimate of your population mean, is to take the sample mean. So yeah, quite intuitive, but it is satisfying to get to there mathematically. Right? Okay, so good, we've done that. Let's look at solving equation 2. So hopefully we can solve for sigma squared. So we can find the best estimator for sigma squared. So I'll copy equation 2. We've got 0 equals, so it's just this equation here, negative n onto sigma hat squared plus 1 onto sigma hat to the 4 sum j equals 1 to n of xj minus, and then what are we subtracting? We subtract mu hat. But since we already found that mu hat is equal to x bar, the sample mean, I'm just going to substitute in the sample mean here. Right? So sort of substitute it in because these equations have to both be true at the same time for you to maximize the function. If you think to sort of Math 1052 techniques, then a multivariate function is maximized when all of its partial derivatives are equal to 0. So they have to be both true at the same time. So I substituted it into here, so we get this equation. And this is something that I can solve to find a value for mu hat. Okay, so to solve this, we can add this term to the other side. So 1 onto sigma hat squared is equal to 1 onto sigma hat to the 4, sum from j equals 1 to n of xj minus x bar squared. And then let's see what we can do here. I might multiply the 2 sigma hat to the 4 to the other side, and I might divide the n as well. So I'll do that in the same step. So we multiply the 2 sigma hat to the 4, and then we still got this, and then we got the 1 on n over here. Sum j equals 1 to n of xj minus x bar squared. Okay, and then we can cancel the 2's here. They cancel. And then the sigma to the 4 over sigma to the 2, that just leaves us with a sigma hat squared is equal to 1 on n, sum from j equals 1 to n of xj minus x bar squared, which is great. This is what you would, at least what I hope you would sort of expect that the standard deviation is, that your best guess for the standard deviation is just to take the sort of sample standard deviation here. You will notice something very important, or something important to notice, is that the MLE here is equal to the biased sample standard deviation. So if you've done some statistics, you might know that usually when you calculate the sample standard deviation, you don't divide by n, but you divide by n minus 1. However, it turns out that the maximum likelihood estimate is actually to divide by n, so it's actually slightly biased.